Good morning, everyone. My name is Carlos Navarro from the University of Seville. I'm going to present this work done in collaboration between the group of mechanical engineering and the Advanced Center of Aerospace Technologies, also in Seville. As we all know, additive manufacturing has many advantages with weight reduction, grouping of several pieces in one, customized fabrication, medical industry. Well, it has many advantages and with, in general, good monotonic properties. But it has also some disadvantages. Our main interest is in fatigue. So we have residual stresses, anisotropy, surface roughness defects, and we focus mainly on surface roughness and defects. These two features may initiate earlier the crack, and we are mainly interested in fatigue life estimation. So we want to see how this affects the fatigue life. Usually, we divide fatigue life between initiation and propagation phases. The difference, the boundary between them is somewhat arbitrary, but we know that initially we have a nucleation and early growth of a crack, and then the crack growth until failure. So when we have these defects, internal defects, and roughness, we ask ourselves if, in this case, the initiation phase could be negligible, and we could ignore this in the fatigue life estimation. We are involved in several research projects, and we found ourselves doing fatigue tests with a different set of specimens coming from different machines and manufacturers, and also with different load ratios. So with all these results, we were thinking about this problem in fatigue life. And also, since we have specimens coming from different machines, as we know, we have many different parameters in the manufacturing of these pieces. Each machine have different parameters, or may have different parameters. Even with the same machine and different laboratories, they may choose different values of these parameters. So this also influences life. And this is also something that we wanted to see in this study. So these are the two objectives of this work. To see the influence of the manufacturer, we have 3 different sets for the same material: layer thickness, thermal treatment, and sandblasting. The rest of the parameters, we guess that are different, but we don't know because the companies didn't want to share that information. And the other, actually, the main objective is to see the influence of the load ratio and study the importance of the initiation and propagation life. These are the 3 machines that fabricated the samples. We call it Erena, EOS 1 and EOS 2. We did first tensile test. We see here in the graph the average curve for each machine having more or less similar values. The roughness was influenced by the sandblasting, but was not very different between these 3 groups. And we did the fatigue test. In this graph, well, this is the specimen that we used. We tested them at more or less at 110 Hertz. And these are the results. We see that they are more or less the same. One group is better for maybe this region, another one is better for this region, but they are all more or less the same, similar, though. So we saw that the influence of the machine was not too big, which is something good. Analyzing all this data in terms of where the failure started, we made this classification where we have defects starting from we have failures starting from an internal defect, failures starting from a defect that was very close to the surface, and failures that started from the surface. As we can see here, the solid circles are the failures started from the surface. The open black circles starting from a defect close to the surface, and the red circles started from an internal defect. As we can see in the graph, there is this transition point where these failures here started from either the surface or a defect very close to the surface. And in this region, about 1 million cycles, we have almost all of them started from an internal defect. This behavior reminds us of regular materials, where if we go to the gigacycle zone, we have the typical failures starting with the eye fish feature. So this is what we see here, but maybe in starting earlier. We guess that when the manufacturing process improves, this transition point will move to the right. In any case, we see all this distribution, and now we want to see how the failure started from this usually in defects, and how it affects the total life. We have to compare this. We have these two sets of tests. The blue ones with a load ratio of -1, and the red one with a load ratio of 0.1. In this graph, we have here the amplitude of the stresses. So, of course, these two sets of data, they do not match. So now we want to see if using different criteria, we can make these two sets of data collapse together. So we tried first the typical criterions like Goodman, for example. Here, where we see that they are closer together, but well, we have the red line is a fit to the results of the 0.1 group, the blue one for the -1, and the black line is a fit to all the data. And here we have also the fitting of the correlation parameter, which is very low, 0.5. So actually this is bad. So this is with the Goodman. Here, this one is Soderbergh, which is very similar to Goodman, and it's also bad. We use Gerber, and it's even worse, 0.3. We use Smith-Wasson-Topper, slightly better, but still not good. And finally, we tried the Walker criterion with this equation, and uses this fitting parameter that we see here, almost 1. And in this case, the two group of tests, they collapse into each other. And the coefficient here is 0.8. And we did another one, which is this one, which is taking as the parameter the positive part of the range of the stress cycle. The result is also very good, maybe slightly worse than this one, but it's very, very good. And the conclusion that we draw from here is that this reminds us of what we do when we model crack propagation, where in a first step, if we ignore the crack closure, we take the positive part of the strain of the stress intensity factor range to correlate the crack growth rate. So in this case, what we see is that using the positive part of the strain range make these two very different group of tests collapse. So what we think is that in this case, the initiation phase is almost negligible, and we can ignore this and use only a propagation model to estimate the fatigue life. Even if we think this happens in all the range of this test, and if we go back here, it's working also in this region where we have failures starting from the surface, also defects very near the surface, but also from the surface. So maybe when we say that the failure started from the surface, it was really a defect, but maybe too small to see and characterize it as a defect. But in any case, this one works very well. So my conclusions were that there are some differences in mechanical properties between machines, but not relevant. It has been observed a change in where the crack initiates between low fatigue and high cycle fatigue. And we think that in the initiation phase, the initiation phase can be neglected when we estimate the fatigue life. And this is my acknowledgements. So thank you very much for your attention.
Thank you very much for the very nice presentation. We have time for a couple of quick questions. Yes.
Thank you very much for your nice talk. My question regards the use of a resonant testing machine, so in which you are able to monitor the natural frequency of the test. So do you...
I cannot hear you well. I don't...
My question regards the use of a resonant testing machine, right? In which resonant testing,
okay.
a rumor.
Yeah.
Okay, so did you detect a drop in the frequency already after the start of the test?
The test was stopped when the failure was produced. The frequency changed at the end of the test, but it was very close to the end. So there was not relevant difference in the number of cycles if we stopped it when this change happened.
Okay, thank you.
I have also a quick question regarding the surface quality that we could get from different machines. If I understood correctly, you sandblasted all samples, so you started from the surface quality, or you had the different surface roughnesses induced by each machine?
No, we did the sandblasting after they manufactured the specimens.
On all samples?
All the samples, yeah.
So on all samples, you started from the same surface softness?
Yeah.
Okay.